There was a time when the universe had no stars, no constellations crossed the sky, no galaxies gathered into spirals or broad islands of light. There were no planets, no moons, and no distant suns sending their glow across the space between them. The universe was already hundreds of thousands of years old, yet almost everything that would one day make the cosmos visible had not begun to shine. Space itself was expanding. With every passing age, matter became more widely separated, while the temperature of the background continued to fall. The young cosmos was changing everywhere, though almost none of that change could have been seen by human eyes. This was not the beginning itself. The first bright heat of the Big Bang had already faded and expanded. Matter had cooled enough for electrons to settle around atomic nuclei, forming mostly neutral hydrogen, with helium mixed through it. Light that had once scattered constantly through the hot plasma could now travel freely. That ancient light still surrounds us today as the cosmic microwave background. After it was released, the universe entered a long interval that astronomers call the cosmic dark ages. The name can sound more dramatic than the reality. Space was not empty, and it was not without radiation. The faint afterglow of the early universe continued everywhere. Gravity was also at work, drawing matter toward regions that were only slightly denser than their surroundings. But there were no stars yet, and without stars, there was almost no visible light being made. For tens of millions of years, hydrogen filled the growing universe, while small differences in density slowly became more important. Dark matter gathered first into invisible concentrations. Ordinary gas followed its gravity, falling into these early structures and compressing as it moved. Nothing happened quickly by human standards. The change unfolded through ages for which no direct witness could have existed. Then, somewhere in that dim cosmos, the first stars formed. Their arrival did more than add a few points of brightness. These early suns began changing the material around them. Their ultraviolet light carried enough energy to separate electrons from neutral hydrogen atoms, turning the gas back into an ionized state. At first, each star or young galaxy affected only a small region. Around every source of strong radiation, a bubble of ionized hydrogen expanded into the surrounding neutral medium. Across the universe, more bubbles appeared. They grew around early galaxies, met neighboring bubbles, and slowly connected. The change did not pass through space like a single wave. It happened unevenly wherever stars and galaxies had formed strongly enough to alter their surroundings. Some regions became transparent to ultraviolet light earlier. Others remained neutral for much longer. This drawn-out transformation is known as cosmic reionization. It marks one of the largest changes in the history of the universe, yet much of it remains difficult to observe directly. The first stars were faint, distant, and short-lived. Their light has been stretched by cosmic expansion for more than 13 billion years. The hydrogen between those early sources absorbed much of the radiation that might otherwise have reached us. And so the end of the cosmic dark ages is not a single moment preserved in one clear image. It is a transition reconstructed from traces, old light, distant galaxies, the absorption patterns of hydrogen, and the background radiation left from an even earlier time. Tonight, we will move through that transition, from a universe without stars to one filled with the first growing networks of light. The darkness did not end all at once. It opened region by region. The long interval after the cosmic microwave background was released was not truly still. Beneath its apparent emptiness, the universe carried a faint pattern left from its earliest moments. Some regions contained slightly more matter than others. The differences were tiny, but gravity does not need a large beginning. It only needs time. Where there was a little more mass, the pull became a little stronger. Nearby material moved inward. The denser region grew denser still. Dark matter played a central role in this process. Unlike ordinary matter, dark matter did not interact with light in the usual way. It did not need to cool by emitting radiation before gravity could gather it into structure. As the universe expanded, dark matter began collecting into small halos, invisible frameworks that formed before the first stars. Ordinary hydrogen and helium then fell toward these concentrations, drawn into wells of gravity that had already begun to deepen. At first, the gas remained too warm and too diffuse to form anything like a star. Falling inward compressed it, and compression raised its temperature. For collapse to continue, some of that energy had to escape. The gas needed a way to cool. In the modern universe, cooling often depends on heavier elements such as carbon, oxygen, silicon, and iron. Their atoms and ions can radiate energy efficiently across many wavelengths, but those elements did not exist during the Dark Ages. The first gas contained almost nothing beyond hydrogen, helium, and a trace amount of lithium. There were no grains of interstellar dust, no oxygen-bearing molecules, no carbon chemistry spreading through clouds. The material from which the first stars would form was chemically simple in a way that no large star-forming cloud is today. Hydrogen molecules offered one of the few available paths forward. Most hydrogen existed as individual atoms, but in the growing dark matter halos, a small fraction could form pairs. Molecular hydrogen was not an especially efficient coolant, yet it could release enough energy to lower the temperature of the gas and allow gravity to compress it further. The first star-forming regions were likely small by galactic standards. Astronomers often call them mini-halos. They contain dark matter, primordial gas, and no previous generation of stars. Within them, matter gathered slowly toward the center, passing through stages that computer simulations now attempt to reconstruct. As the central gas became denser, its behavior changed. Cooling and gravity competed with pressure. The cloud did not necessarily remain smooth. Parts of it could rotate, flatten, fragment, or feed material toward a growing core. The exact details remain an active area of research because no telescope has yet recorded the birth of an individual first star. Even so, the broad sequence is supported by well-tested physics. A dense core formed. Gravity pulled more gas toward it, temperature and pressure rose. At some point, the center became dense enough for nuclear fusion to begin. Hydrogen nuclei started combining, releasing energy, and a star appeared where no star had existed before. This first generation is usually called Population 3. The name comes from an older astronomical classification. Population 1 stars, like the Sun, contain relatively large amounts of elements heavier than helium. Population 2 stars are older and more chemically primitive. Population 3 refers to the hypothetical first stars, formed from material untouched by earlier stellar generations. No Population 3 star has been directly confirmed. They belong to a period so distant that observing them individually remains beyond current limits. Their expected properties come from simulations, chemical models, and the effects they may have left behind. Many models suggest that at least some were far more massive than the Sun, perhaps because primordial gas could not cool and fragment as readily as the enriched gas of later eras. But the first stellar population may not have followed a single pattern. Some simulations produce very massive stars. Others allow smaller companions or groups to emerge within the same collapsing system. Rotation, turbulence, magnetic fields, and the flow of gas through an early disk may all have shaped the final result. What matters most for the larger story is that these stars were luminous, hot, and short-lived. A massive first star could produce intense ultraviolet radiation. Its light began changing the surrounding hydrogen almost immediately. Close to this, energetic photons stripped electrons from atoms, creating a growing region of ionized gas. Farther away, other wavelengths altered the chemistry of nearby clouds, sometimes encouraging molecular hydrogen to form and sometimes breaking it apart. The first light, therefore, did more than illuminate space. It changed the conditions under which later stars could form. Every newborn sun entered a universe that had never hosted a sun before. There were no old stellar winds passing through the gas, no supernova remnants expanding from earlier generations, and no background of heavy elements scattered across the region. Each object was beginning a new physical era. Their lives may have ended quickly. The most massive stars consume their nuclear fuel at a remarkable rate. Some first stars may have collapsed directly into black holes. Others may have exploded as supernovae, releasing the first substantial supply of heavier elements into space. Under certain conditions, a star could have been disrupted completely in a pair instability supernova, leaving no compact remnant behind. Those endings mattered as much as the first ignition. Inside stellar cores, fusion created new nuclei. Explosions and outflows carried them into the surrounding gas. Carbon, oxygen, silicon, and iron began entering regions that had previously contained almost none. The chemical simplicity of the universe was ending. Later clouds could cool in new ways. They could fragment into smaller pieces. New generations of stars could form with different masses and longer lives. Around some of those later stars, disks rich in heavier elements would eventually provide the material for rocky planets. None of that happened everywhere at once. The first stars appeared in scattered pockets, separated by great distances. Between them, most of the universe remained neutral and unlit. A single star might brighten one small region, while an immense volume beyond it continued through the dark ages unchanged. Then, more halos collapsed, more stars formed. Small systems began merging into larger ones. The isolated points of first light became clusters of activity, and those clusters became the earliest galaxies. The universe was not yet transparent to all of their radiation. Neutral hydrogen still filled the space between them, absorbing much of the ultraviolet light these young objects produced. Each source could open only a limited region around itself. Beyond that boundary, the old darkness remained. The end of the dark ages had begun, but the work of ending them would belong not to one star, nor even to one generation. It would belong to the first galaxies. The first galaxies did not resemble the large spirals that fill modern telescope images. They were smaller, more irregular, and still in the process of gathering themselves. Their stars formed inside shallow wells of gravity, where dark matter, gas, and radiation were locked in a delicate exchange. Some systems may have contained only a few million stars. Others were little more than bright knots surrounded by streams of hydrogen. Yet these early galaxies changed the universe more effectively than isolated stars could. A single massive star could ionize the gas around it, but its influence faded when the star died. A galaxy provided continuity. New stars formed as older ones reached the ends of their lives. Clusters of hot young suns produced a steady supply of ultraviolet photons. Supernovae stirred the gas, opening channels through which some of that radiation could escape into intergalactic space. The amount that escaped was important. Most ultraviolet light born inside a galaxy did not travel freely outward. Dense clouds absorbed it. Dust was almost absent in the earliest systems, but neutral hydrogen alone could stop photons energetic enough to ionize another hydrogen atom. For a galaxy to help end the cosmic dark ages, part of its radiation had to pass beyond the gas in which its stars had formed. Astronomers described this with a quantity called the escape fraction. It is the fraction of ionizing photons that leave a galaxy and enter the wider universe. If the escape fraction is low, even a bright galaxy may change only its immediate surroundings. If it is higher, the same galaxy can carve a growing bubble into the neutral hydrogen beyond it. The value was probably not the same everywhere. Young galaxies were unstable. Their star formation came in bursts. Gas fell inward along filaments. Stellar winds and supernovae pushed material outward. A region could be opaque at one moment, then become more transparent after an explosion cleared a path through it. The escape of radiation may have varied over thousands or millions of years, even within a single galaxy. This made reionization an irregular process from the beginning. Imagine a wide field covered in mist before sunrise. A light appears in one place, then another, but the mist does not lift evenly. Some patches thin quickly, others remain dense. The edges shift with every new source and every change in the air. The early universe was not a landscape, and neutral hydrogen was not earthly fog, but the comparison carries one useful idea. The first galaxies did not simply brighten a dark background. They altered how far light could travel through it. Around every active galaxy, ionized hydrogen formed a bubble. Near the stars, electrons had been stripped from atoms. Farther away, beyond the reach of enough ultraviolet radiation, the gas remained neutral. The boundary between these regions was not a hard shell. It was a moving transition shaped by the brightness of the galaxy, the density of nearby matter, and the presence of other galaxies close enough to contribute their own light. At first, the bubbles were separate. A galaxy might live inside a region of ionized gas spanning thousands of light years, while the space beyond remained mostly neutral. As more galaxies formed, nearby bubbles began to overlap. Several small systems could create a shared region larger than any one of them could maintain alone. This is where the structure of the universe began to matter. Matter was not distributed evenly. Dark matter gathered into filaments, sheets, and dense intersections. Gas and galaxies followed that underlying framework. The first luminous systems, therefore, tended to form near one another, in the parts of the cosmic web where gravity had collected the most material. Reionization began earlier in these crowded regions. Clusters of small galaxies produced overlapping zones of ionized gas. The bubbles expanded outward from the densest parts of the cosmic web, joining across the spaces between them. More isolated regions, especially those far from strong sources of ultraviolet light, remained neutral longer. The transformation moved from structure into emptier space. This inside-out pattern is one of the leading ways astronomers understand the era. Dense regions formed galaxies first, even though they also contained more hydrogen to ionize. Their abundance of stars gave them enough radiation to overcome that extra material. Less dense regions had less gas, but also fewer galaxies, so their change could be delayed. The process did not have a single center. There was no special place where the universe first became transparent, and no outer frontier moving steadily away from it. The same sequence unfolded in countless regions at once. Each one followed its own local conditions while contributing to a transformation that eventually reached across the observable cosmos. The galaxies responsible were probably faint by modern standards. For many years, astronomers focused on the brightest early galaxies because those were the easiest to detect. But the known bright systems alone may not have produced enough ionizing radiation to complete reionization. Much of the work may have been done by smaller galaxies below the limits of earlier surveys. Individually, they were weak. Together, they may have been dominant. A large population of small galaxies could create more total ionizing light than a rare population of brilliant ones. Their stars formed rapidly, and their shallow gravity allowed supernovae to disturb their gas more easily. That disturbance may have helped open paths for radiation to escape, but shallow gravity also made them fragile. A burst of star formation could drive gas out of a small galaxy. Ultraviolet radiation could heat surrounding material and prevent fresh gas from falling inward. Some systems may have brightened briefly and then faded, unable to sustain new stars until more matter arrived. Their contribution came in pulses. Across millions of years, one galaxy turned on while another quieted. A cluster of stars appeared, flooded its surroundings with ultraviolet light, and then vanished into remnants. The combined effect was steadier than any single source, yet the local universe remained restless. The light reaching us from these galaxies has been traveling for more than 13 billion years. While you rest beneath a much older sky, telescopes collect photons that left their sources when the universe was only a small fraction of its present age. Those photons have crossed expanding space, their wavelengths stretched from ultraviolet and visible light into the infrared. They do not arrive carrying a complete picture. A distant galaxy may appear as a faint red smudge, containing light from many stars blended together. Its shape can be difficult to resolve. Its distance must be inferred from the way cosmic expansion has shifted its spectrum. The hydrogen around it may absorb part of what it emitted, especially at wavelengths connected to the ionization process. Astronomers most want to understand. Even so, each detection adds another point to the map. The number of galaxies at a given age tells us how quickly structures were forming. Their brightness suggests how many stars they contained. Their colors reveal the ages of those stars and the presence of gas. Spectra can show oxygen, hydrogen, and other elements, offering clues about how rapidly the first generations enriched their surroundings. The earliest known galaxies already contain complexity. They show that star formation began early and that chemical evolution could proceed quickly. Some appear compact and intense. Others are spread into multiple knots, perhaps because small systems were merging. A few host-active black holes, whose feeding disks add another source of energetic radiation. Black holes may have helped, though their total role remains uncertain. As matter fell toward an early black hole, it heated and produced ultraviolet and X-ray light. X-rays could travel farther through neutral hydrogen than ordinary ionizing ultraviolet photons. Instead of creating sharply bounded bubbles, they may have warmed broad regions of intergalactic gas and partially ionized them. This warming changed the background against which later stages unfolded. Before widespread heating, hydrogen gas could be colder than the radiation left from the Big Bang. As stars, galaxies, and black holes appeared, their radiation raised the temperature of the intergalactic medium. The universe was not only becoming ionized, it was also being heated. These two histories were connected but not identical. Some regions warmed before they became fully ionized. Others experienced repeated changes as new sources appeared. The timing depended on the mixture of starlight, X-rays, gas density, and distance from active galaxies. By the time the first galaxies had become common, the Dark Ages were no longer complete. Large volumes of space still contained neutral hydrogen, but the old uniformity had been broken. The universe had become a patchwork of luminous sources, heated zones, ionized bubbles, and untouched regions waiting farther away. Every new galaxy widened the openings. Every merger gathered more matter into the places where stars could form, and through the expanding web of early structure, the separate islands of light began finding one another. The light from the first galaxies does not reach us untouched. Before it can cross the universe, it must pass through whatever lies between its source and our telescopes. During reionization, much of that intervening space was filled with neutral hydrogen. The atoms were nearly invisible in one sense because they did not shine brightly on their own. Yet they could leave a clear mark on any light that traveled through them. This is one of the central ways astronomers study an era they cannot photograph directly. A spectrum spreads light into its component wavelengths. Instead of seeing only a faint point or a dim patch, astronomers examine how much light arrives at each wavelength. Bright regions in the spectrum can reveal emission from hot gas. Dark gaps can show where certain wavelengths were absorbed along the way. Hydrogen has a particularly important pattern. When an electron in a hydrogen atom changes energy, it can absorb or emit light at specific wavelengths. One of the strongest transitions is known as Lyman-Alpha. In the laboratory, it lies in the ultraviolet. But light traveling through an expanding universe is stretched toward longer wavelengths. So ancient Lyman-Alpha can arrive at modern telescopes in visible or infrared light. The amount of stretching carries information about cosmic time. A galaxy seen at high redshift is being observed when the universe was young. By measuring where known spectral features appear, astronomers can estimate when its light was emitted. Neutral hydrogen between the source and Earth absorbs light near the Lyman-Alpha wavelength. Because each cloud of hydrogen lies at a different distance, each one absorbs a slightly different part of the traveling spectrum. The result can resemble a forest of narrow dark lines, each marking a separate region along the line of sight. Astronomers call this the Lyman-Alpha forest. At later cosmic times, when most intergalactic hydrogens was already ionized, the forest is broken into many distinct features. There is enough neutral hydrogen left to create absorption, but also enough transmitted light to separate one feature from another. Looking farther back changes the pattern. As the fraction of neutral hydrogen increases, the dark regions become wider and more frequent. Less light passes through. Near the end of reionization, some spectra contain long stretches where almost no light is transmitted at all. These broad dark intervals are often called absorption troughs. They do not mean that every atom along the path was neutral. Lyman-Alpha absorption is so sensitive that even a small neutral fraction can remove nearly all the light at the relevant wavelengths. This makes the method powerful, but it also makes interpretation difficult. A black region in a spectrum does not directly reveal the exact amount of neutral hydrogen. It tells astronomers that enough was present to make the path opaque. The first major clue came from quasars. A quasar is the intensely luminous center of a galaxy, where matter is falling toward a supermassive black hole. Gas in the accretion disk becomes hot and radiates across a wide range of wavelengths. Because quasars can be far brighter than their host galaxies, they act as distant background lamps. When a quasar shines through the intergalactic medium, its spectrum carries a record of the material between it and us. In the early 1960s, James Gunn and Gunn-Peterson described how a universe containing widespread neutral hydrogen should produce a deep absorption feature in the spectra of very distant objects. Decades later, telescopes became powerful enough to observe quasars from the final stages of reionization, and some of their spectra showed the expected suppression. The feature became known as the Gunn-Peterson trough. Its appearance helped establish that the universe near a redshift of about 6 was different from the more transparent universe seen at later times. But it did not provide a single clean date when reionization ended. Different quasars showed different levels of transmission. Some lines of sight contained long dark gaps. Others allowed more light through. That variation was not a flaw in the measurement. It was part of the story. Reionization was patchy. One quasar's light might cross a region that had been ionized early by many nearby galaxies. Another path might pass through a more isolated area where neutral hydrogen survived longer. Two quasars from nearly the same cosmic age could therefore carry different absorption patterns. The universe was becoming transparent unevenly. This makes every spectrum a narrow sample through an enormous volume. A single line of sight is like one slender core taken through deep ice. It preserves a sequence, but not the whole landscape. To reconstruct the larger history, astronomers need many quasars, many galaxies, and many independent methods. Quasars are rare at the earliest times, and the most distant ones are difficult to find. Their spectra require long observations, and the quasar itself can influence nearby gas. Its radiation creates an ionized region known as a proximity zone. Close to the quasar, hydrogen may be transparent because the quasar has stripped electrons from nearby atoms. Farther away, the wider intergalactic medium leaves its absorption pattern. The size and shape of the proximity zone can reveal something about the quasar's age, brightness, and surroundings, but these factors must be modeled carefully before the broader hydrogen signal can be understood. Galaxies provide another view. Unlike quasars, early galaxies are more numerous, and they were probably the main sources driving reionization, but they are much fainter. Their Lyman-Alpha emission can be weakened or erased by neutral hydrogen around them. When more Lyman-Alpha emitting galaxies are visible at a certain epoch, it suggests that their light had relatively clear paths through ionized space. When fewer are seen farther back in time, one explanation is that neutral hydrogen was more abundant and scattered those photons before they could escape. The interpretation is not automatic. A galaxy's own gas can absorb Lyman-Alpha. Dust can affect it. Outflows can shift the line in wavelength, helping some photons pass through surrounding hydrogen. The galaxy's shape, star formation, and local environment all matter. Yet, across large samples, changing visibility becomes another clue to the progress of reionization. Astronomers also look for damping wings. Neutral hydrogen can absorb light not only at the exact center of the Lyman-Alpha line, but across a broader range around it. This extended absorption can appear as a wing in the spectrum of a distant galaxy, quasar, or gamma-ray burst. A gamma-ray burst can briefly provide another bright background source. Some bursts occur when massive stars collapse. For a short time, their afterglows can shine the galaxies that contain them. If one appears at a great enough distance, its spectrum may preserve information about neutral hydrogen both inside its host galaxy and in the wider universe. These events fade quickly, but each suitable burst can offer a rare independent line of sight. All these methods share a basic idea: the missing light matters. Astronomers do not only study what arrives, they study the shapes cut into it, the wavelengths that disappear, and the intervals where transmission returns. The dark regions are not empty measurements. They are records of atoms that stood between an ancient source and detector, built billions of years later. There is a long human thread in this kind of observation. For centuries, people learned about distant objects by separating light. Prisms showed that white light contained color. Later spectroscopes revealed dark lines in sunlight and bright lines in gases. Those principles now reach into a period before the Milky Way had taken its modern form. The scale has changed, but the method remains recognizable. A photon encounters hydrogen. A specific wavelength is removed. The surviving light continues across expanding space. Much later, a mirror gathers it, a detector counts it, and a spectrum turns that absence into evidence. No one sees the neutral hydrogen directly along the full path. Instead, its presence is inferred from the way it shaped something else. This is common in astronomy. Dark matter is mapped by gravity. Black holes are traced by motion and radiation around them. The early intergalactic medium is studied through the light it prevented from reaching us. By combining many spectra, astronomers can estimate how opacity changed with time. The results suggest that reionization was well advanced by the time the universe was around 1 billion years old, while substantial neutral regions existed earlier. The transition stretched across hundreds of millions of years rather than occurring in one sudden event. Its final stages may have been especially uneven. Ionized regions surrounding clusters of galaxies expanded and connected. Neutral islands remained between them, shrinking as ultraviolet radiation reached deeper into their boundaries. Some survived in underdense or remote regions after nearby areas had become transparent. A spectrum passing through one of these islands could lose a long segment of light. Another spectrum, traveling through a connected ionized region, might preserve much more. The pattern is therefore both temporal and geographic. It tells us when the universe changed and how differently that change unfolded from place to place. Yet absorption alone cannot reveal everything. Once Lyman-Alpha becomes saturated, a mostly neutral region and a much less neutral region can both appear nearly black. The method loses sensitivity precisely where the hydrogen abundance becomes high. It can show that the universe was opaque without measuring every degree of that opacity. To go deeper into the dark ages, astronomers need a signal produced by the hydrogen itself. Neutral hydrogen has such a signal. It comes not from visible light or ordinary ultraviolet emission, but from a faint radio transition associated with the relative alignment of the proton and electron inside each atom. In its original frame, the wavelength is about 21 centimeters. Cosmic expansion stretches that signal as well. Hydrogen from earlier times should appear at longer radio wavelengths today, carrying a three-dimensional record of where neutral gas was cold, where it was heated, and where it had already been ionized. The signal is weak. Earthly radio interference is strong. Our own galaxy shines brightly across the same frequencies. Separating the cosmic pattern from the foreground requires precision on a remarkable scale. But unlike a quasar spectrum, which follows one narrow path, the 21 centimeter signal could map whole volumes. It could reveal the shapes of ionized bubbles. It could show the remaining neutral islands between them. And if the measurements become clear enough, it may allow astronomers to watch the end of the Dark Ages not as a collection of shadows in distant light, but as a changing structure spread across the young universe. The 21 centimeter signal begins with an atom so simple that it seems almost incapable of carrying the history of the universe. A hydrogen atom contains one proton and one electron. Both have a quantum property called spin. When their spins are aligned in the same direction, the atom holds a tiny amount more energy than when they point in opposite directions. If the alignment changes, the atom can release a photon with a wavelength of about 21 centimeters. For a single atom, this transition is rare. A lone hydrogen atom might wait millions of years before emitting such a photon. But the early universe contained an immense number of hydrogen atoms spread through nearly every region of space. Together, they could produce a faint radio glow that traced where neutral gas remained. The signal was never bright. Even before it began crossing the universe, it was delicate. Cosmic expansion then stretched its wavelength farther, moving it into parts of the radio spectrum where signals from our own galaxy, distant radio sources, satellites, aircraft, and human communication can be far stronger. Still, the information carried by those photons is unusually rich. Unlike visible light from a galaxy, which tells us mainly about the place where stars formed, 21-centimeter radiation can arise throughout the hydrogen between galaxies. In principle, it can reveal broad volumes rather than isolated points. It can show where gas was colder than the background radiation, where it had been heated, and where it had disappeared into ionized bubbles. To understand that record, astronomers follow a quantity called the spin temperature. The name does not describe the ordinary motion of the gas. It describes how the hydrogen atoms divide themselves between the two spin alignments. If the spin temperature matches the temperature of the cosmic microwave background, the hydrogen leaves almost no visible imprint against that background. The atoms absorb and emit at nearly equal rates, and the signal becomes difficult to distinguish. If the spin temperature falls below the background temperature, the hydrogen can appear in absorption. If it rises above the background, the hydrogen can appear in emission. This creates a changing sequence across cosmic history. Soon after neutral hydrogen formed, interactions among atoms helped connect the spin temperature to the temperature of the gas itself. As expansion continued, the gas cooled more rapidly than the cosmic microwave background. For a time, that allowed hydrogen to absorb some of the background radio light. Later, the universe became more diffuse. Collisions were less effective, and the spin temperature drifted back toward the microwave background. The absorption weakened. Then the first stars appeared. Their ultraviolet radiation introduced a new connection. Photons near the Lyman-Alpha transition scattered through the hydrogen and repeatedly changed the internal states of the atoms. Through a process known as the Wolff-Usen field effect, the spin temperature could once again become coupled to the physical temperature of the gas. By then, the gas was colder than the microwave background. The result should have been a deeper period of 21-centimeter absorption, spread across the era when the first starlight began reaching the intergalactic medium. This stage links atomic physics with the birth of stars. A signal measured at a particular radio frequency can correspond to hydrogen at a particular redshift. Lower observed frequencies generally point to earlier times, because the original 21-centimeter wavelength has been stretched more by expansion. By scanning across frequency, astronomers are not merely tuning a radio receiver, they are moving through layers of cosmic history. At one frequency, the signal may come from a time before abundant stars. At another, it may trace the first ultraviolet radiation. Farther along, it may show the gas being warmed by X-rays from stellar remnants, compact binaries, or feeding black holes. Later still, it may reveal the advance of ionized bubbles around galaxies. The broad average of this signal across the whole sky is called the global 21-centimeter signal. It does not show where individual structures were located. Instead, it traces how the average state of hydrogen changed with time. The expected pattern is not a single dip or rise. It is a sequence. First, weak absorption, then a deeper absorption feature as the first stars couple the spin temperature to cold gas. After that, a gradual recovery as X-rays and other sources heat the hydrogen. Eventually, emission may appear if the gas becomes warmer than the microwave background. Finally, the signal fades as reionization removes most neutral hydrogen from the intergalactic medium. Each turn in that pattern corresponds to a physical transition. The depth of the absorption can reveal how cold the gas became. Its timing can constrain when the first stars formed. The shape of the recovery can indicate how efficiently early sources heated their surroundings. The disappearance of the signal can trace the progress of reionization. But the global signal is buried beneath foreground radiation many thousands of times brighter. Our galaxy produces strong radio emission from electrons moving through magnetic fields. That foreground is smooth across frequency compared with the expected cosmological signal. which gives astronomers a possible way to separate them. Yet a radio antenna, its surrounding ground, the ionosphere above it, and the electronics connected to it can all introduce their own frequency-dependent patterns. A small instrumental feature can imitate a cosmic one. A reflection in a cable can create a ripple. Temperature changes can alter the response of a receiver. Radio waves can bounce from the ground or nearby structures. The ionosphere can bend and absorb low-frequency signals in ways that shift over the course of a night. This is why some experiments are placed in remote regions. Far from cities, mobile towers, and dense communication networks, the radio sky is cleaner. Even there, complete isolation is impossible. Satellites cross overhead. Distant transmitters can reflect from the upper atmosphere. Lightning and electrical equipment can leave brief signatures. The instruments must therefore be understood with great precision. A simple-looking antenna may be modeled through every frequency of interest. Researchers measure how it responds to the sky at different angles. They track the temperature of its components. They compare observations from many nights and remove periods affected by interference. The cosmological signal is not found by turning up the gain. It is found learning what every other part of the measurement is doing. Another approach looks not at the average sky, but at variations from place to place. Arrays of many radio antennas can work together as an interferometer. Instead of producing one global curve, they measure spatial fluctuations in the 21-centimeter brightness. These fluctuations can reveal the patchwork structure of heating and ionization. Early in cosmic dawn, some regions may have been coupled strongly to starlight, while others had not yet been reached. Later, X-ray heating may have created warm zones around the first compact sources. During reionization, ionized bubbles would appear as places where the 21-centimeter signal vanished, surrounded by neutral gas that still emitted or absorbed. The pattern would change in both scale and contrast. Small bubbles would appear first around individual galaxies or groups. As more sources formed, those regions would expand and merge. The characteristic size of the structure would grow. Toward the end, neutral hydrogen would survive in shrinking islands between connected ionized regions. Radio arrays try to detect this statistical pattern before they can make a detailed image. They measure how strongly the signal varies across different angular scales. Large fluctuations may indicate broad ionized regions. Smaller fluctuations can reflect the distribution of galaxies, density differences in the gas, and uneven heating. The interpretation requires models. The same observed pattern might be influenced by several factors at once. The brightness of early galaxies, the escape of ultraviolet radiation, the abundance of X-ray sources, the masses of the halos forming stars, and the way matter was distributed through the cosmic web. No single measurement can settle all of them, but a sequence across many frequencies can narrow the possibilities. So can comparisons with galaxy surveys, quasar spectra, and the cosmic microwave background. Each method responds to a different part of the same history. There is a special difficulty in observing this signal from Earth. At the lowest frequencies associated with the deepest part of cosmic dawn, the ionosphere becomes increasingly troublesome. Below certain frequencies, it can block radio waves entirely. Even above that boundary, it changes their paths and adds noise. The far side of the Moon offers a rare environment. For part of each lunar orbit, it is shielded from radio transmissions coming from Earth. There is no ionosphere above the lunar surface. A radio instrument placed there could observe low frequencies that are difficult or impossible to measure cleanly from the ground. Such an observatory would not escape every challenge. The lunar landscape would affect antenna design. Power, communication, dust, and temperature swings would all matter. But the radio stillness of the far side makes it one of the most promising places for reaching farther into cosmic dawn. For now, most of the work remains a patient effort to separate foreground from signal. The universe does not offer this era in a bright image. It offers a faint statistical texture hidden beneath the radio sky. That texture is worth recovering because it may contain a nearly continuous history. Visible telescopes find the luminous objects that formed first. Quasars reveal absorption along narrow paths. The microwave background shows conditions long before stars. 21-centimeter hydrogen can connect these records, filling part of the long interval between them. It can show when the first stars began affecting gas beyond their own halos. It can reveal whether early heating was rapid or delayed. It can trace the growth of ionized regions before they joined into a connected universe. And because the signal comes from hydrogen spread through space, it may eventually allow astronomers to build a map not only of where the first galaxies were, but of what those galaxies did to everything around them. The first light was local. Its consequences were not. Across the young cosmos, each source altered the temperature, chemistry, and visibility of hydrogen far beyond the stars that produced it. The 21-centimeter line preserves those changes in a form so faint that detecting it requires instruments built around restraint. The receivers listen through the noise of the present for a transition within the simplest atom, and hidden inside that transition is the shape of the universe before the darkness was gone. Long before the first stars appeared, another light had already begun crossing the universe. It came from a much earlier transition, when the cosmos cooled enough for electrons and atomic nuclei to join. Once neutral atoms formed, radiation that had been trapped within a hot plasma could move freely through space. That radiation became the cosmic microwave background, a faint afterglow now stretched into microwave wavelengths by more than 13 billion years of expansion. It is the oldest light astronomers can observe directly. The microwave background shows the universe before galaxies, before stars, and before the first black holes began feeding. Its temperature is almost uniform across the sky, but not perfectly. Small variations record the density differences from which later structure grew. Those patterns reveal the starting conditions. The dark matter halos of cosmic dawn developed from them. The gas that formed the first stars followed them. The galaxies that later ionized the universe can be traced, in a distant way, back at faint irregularities in the earliest visible light. Yet the microwave background does not only preserve conditions before the Dark Ages, it also carries a mark left when those Dark Ages began to end. As ultraviolet radiation from early stars separated electrons from hydrogen atoms, free electrons returned to intergalactic space. A microwave photon passing through this ionized material had a small chance of scattering from one of those electrons. Most photons traveled onward without interruption. Some changed direction across the entire sky. This scattering slightly altered the microwave background. The effect is subtle, but it allows astronomers to estimate how much ionized material the ancient light passed through on its journey to us. The measurement is described by a quantity called optical depth. In this context, optical depth expresses the probability that a microwave background photon scattered from a free electron after the original light was released. A larger optical depth would suggest that widespread ionization began earlier, giving photons more time and more free electrons to encounter. A smaller value points toward a later or more gradual transformation. The number does not provide a complete timeline by itself. Different histories can produce a similar total optical depth. Reionization could begin weakly at an early time and continue for a long interval. It could start later and move more rapidly. Small regions might become ionized, partially recombine, and then be ionized again as galaxies grew more numerous across. The microwave background records the accumulated result. It is like knowing the total amount of mist crossed during a long journey without seeing exactly where each bank of mist began or ended. The scattering reveals that free electrons were present along the path, but other observations are needed to place them more precisely in time. One of the most valuable clues comes from polarization. Light can be understood as an electromagnetic wave. Its electric field oscillates in directions perpendicular to its motion. When those directions have a preferred pattern, the light is polarized. The early microwave background acquired polarization through scattering before neutral atoms formed. Later scattering during reionization added a second pattern across very large angular scales. That later signature is faint. It appears most strongly across broad regions of the sky, rather than in small details. Measuring it requires careful control of instrumental effects and a detailed understanding of microwave emission from the Milky Way. Our galaxy fills the sky with foreground radiation. Dust grains aligned with magnetic fields emit polarized microwaves. Electrons moving through galactic magnetic fields produce another polarized component. These signals can be brighter than the ancient pattern astronomers seek. Different frequencies help separate them. The cosmic microwave background has a known spectral shape. Galactic dust and electron radiation change differently with wavelength. By observing the sky in several microwave bands, researchers can model the foregrounds and estimate what remains after they are removed. The process is never as simple as subtracting one clean map from another. The properties of dust vary across the galaxy. Magnetic fields twist along each line of sight. Instrument calibration matters. A small error in detector response can create patterns that resemble real polarization. Large areas of sky must be compared. Independent observing programs test one another. Over time, the measurements have placed tighter limits on the optical depth and, through it, on the broad timing of reionization. The results indicate that the universe did not become fully ionized extremely early. Instead, the main transformation appears to have occurred during the same general period suggested by distant galaxies and quasar absorption. This agreement matters. The methods rely on different physics. Quasar spectra examine neutral hydrogen along narrow paths near the end of reionization. Galaxy surveys count and characterize possible sources. 21-centimeter experiments seek the gas directly. Microwave polarization measures the integrated scattering caused by free electrons. When these approaches point toward a compatible history, confidence grows. Not every detail becomes certain. The average timing may be constrained, while the duration remains less clear. The total optical depth may be measured, while the relative contributions of faint galaxies, bright galaxies, and black holes remain debated. A broad transition can be identified even when its regional structure is still hidden. The microwave background also reveals that reionization could not erase the earlier cosmic pattern. Scattering blurred the light only slightly. If the universe had become densely ionized much earlier, the ancient temperature fluctuations would have been more strongly suppressed. Their survival limits how much free electron scattering could have occurred. The earliest light therefore places boundaries on later events. A pattern formed when the universe was less than 400,000 years old helps constrain stars and galaxies that appeared hundreds of millions of years afterward. The connection spans different physical eras. Before neutral atoms formed, ordinary matter and radiation interacted constantly. During the Dark Ages, the radiation traveled while matter gathered under gravity. When stars appeared, their ultraviolet light returned electrons to space. Those electrons then scattered a small fraction of the original radiation, adding a new mark to a much older signal. The universe did not replace one record with another. It layered them. Astronomers read those layers by looking at temperature, polarization, frequency, and angular scale. A large-scale polarization pattern may contain information about early free electrons. A small-scale temperature variation may reflect the density of matter before stars. Other distortions can be caused by hot gas in galaxy clusters that formed much later. One sky contains all these periods together. Separating them is an act of careful reconstruction. There is a generational quality to this work. One group of observers maps the microwave sky. Another studies distant galaxies. Another builds radio antennas in isolated landscapes. Another develops simulations in which stars, gas, dark matter, and radiation evolve together. No single instrument observes the entire transition. No single career follows every photon from its origin to its detection. Instead, measurements accumulate across decades. A satellite map becomes the starting point for a later analysis. A telescope survey identifies galaxies whose effects are tested against microwave polarization. A theoretical model predicts a signature that a future radio array may attempt to find. The understanding passes from one set of hands to the next. The cosmic microwave background itself has traveled in much the same way, though without intention. It crossed the Dark Ages before any observer existed. It passed through the first ionized regions as galaxies began altering space. It continued through the growth of clusters, the formation of the Milky Way, and the birth of the solar system. Now part of it reaches detectors orbiting Earth or carried high above the atmosphere. The photons are old, but the information they carry was gathered along the way. Some arrived without scattering after their original release. Others encountered free electrons during reionization and changed direction. Together, they preserve both the beginning of the Dark Ages and a faint trace of their ending. The measurement is broad rather than detailed. It does not show the shape of an individual ionized bubble. It does not name the first galaxy that cleared a path through surrounding hydrogen. It cannot tell us which early stars lived long enough to leave black holes, or which disappeared in complete explosions. But it places the era within limit. It tells astronomers that the transformation involved enough free electrons to leave a detectable mark, yet not so many, so early, that the older microwave pattern was lost. Those limits guide models of the first galaxies. If reionization occurred too early in a simulation, the predicted optical depth may become too large. If galaxies produce too few ionizing photons, the universe remains neutral longer than quasar, and galaxy observations allow. If the assumed escape fraction is too low, the bubbles fail to grow quickly enough. The microwave sky becomes a test. Models must account for stars that have never been observed individually, galaxies near the edge of detection, and radiation passing through gas that no longer exists in the same state. The successful histories are those that connect all these traces without forcing one measurement to carry more information than it truly contains. This restraint is part of the science. A low-resolution clue can still be powerful when its limits are understood. The microwave background does not reveal every stage of reionization, but it tells us that the first light left an imprint beyond the galaxies that produced it. The imprint covers the sky. No matter where a microwave telescope points, it receives ancient radiation that has crossed the changing universe. In one direction, the path may have passed through regions ionized early. In another, neutral hydrogen may have survived longer. Most of that local detail has been blended into the broad signal, but the combined effect remains. The oldest observable light remembers the return of free electrons. It remembers a universe becoming transparent again, and within its faint polarization, the Dark Ages leave one more boundary for us to follow. There is another way to approach the end of the Dark Ages. Instead of beginning with the gas between galaxies, astronomers can begin with the galaxies themselves. These early systems were the engines of change. Their stars produced ultraviolet light. Their supernovae disturbed surrounding gas. If reionization was the result, then the galaxies were among its primary causes. The difficulty is that they are extremely far away. Their light has crossed more than 13 billion years of expanding space. During that journey, wavelengths that began in the ultraviolet, or visible part of the spectrum, were stretched into the infrared. A galaxy that once shone with hot blue stars can therefore arrive at our detectors as a faint red source. When astronomers measure how far familiar spectral features have moved, they can estimate the redshift of a galaxy, and, from that, the era in which its light was emitted. But the same expansion that makes the signal informative also makes the source difficult to observe. The galaxies appear small, dim, and often unresolved. Before modern infrared observatories, the earliest known galaxies were usually seen as blurred points with limited detail. Researchers could estimate their brightness and sometimes their distance, but the physical conditions inside them remained uncertain. A faint source might contain a compact burst of star formation, a growing black hole, several merging components, or some combination of all three. Infrared telescopes changed the reach of the search. They were designed to detect light stretched beyond the visible range. With sensitive detectors, stable optics, and long exposures, they could find galaxies from earlier periods than previous surveys had reached reliably. Each faint source is measured through several filters. Its brightness changes from one wavelength to another, creating a rough spectral shape even before a full spectrum is taken. One important clue is the Lyman break. Neutral hydrogen absorbs light below a certain ultraviolet wavelength. When that feature is shifted into the infrared, a distant galaxy can appear in redder filters while nearly disappearing in bluer ones. This sudden change gives astronomers a way to identify high redshift candidates. Candidates are only the beginning. Color alone can be misleading. A dusty nearby galaxy may imitate the appearance of a much more distant one. So can a cool star within the Milky Way. Instrument noise can create faint false sources. Reliable distance measurements often require spectroscopy, where emission and absorption features are identified directly. Spectroscopy takes time. The incoming light may be so weak that a detector must collect photons for many hours. Even then, the spectrum can be sparse. One or two lines may carry most of the usable information. Hydrogen emission reveals active star formation. Oxygen and other elements show that earlier stars have already lived and died, enriching the gas. The shape of the ultraviolet continuum can suggest the age and temperature of the stellar population. In some systems, unusually bright lines hint at energetic environments that ordinary young stars may not fully explain. The first stars formed from nearly pure hydrogen and helium. If an early galaxy already contains oxygen, carbon, or neon, then at least one previous generation must have produced and released those elements. Chemical enrichment began quickly, perhaps within a few million years of the first stars. This does not mean the original stellar population has been found. Population 3 stars remain unconfirmed as individual objects. Their light may be mixed with later generations, and their lives may have been brief. Astronomers search for indirect signs, unusual abundance patterns, strong helium emission, or galaxies with very little evidence of heavier elements. None of these signs is decisive by itself. A young stellar population can produce hard ultraviolet radiation. So can an accreting black hole. Gas geometry can strengthen some emission lines and weaken others. Dust can alter the overall color. The same spectrum may support several physical models. This uncertainty marks the point where the observations have become detailed enough to ask harder questions. How rapidly did early galaxies build stars? How much of their ionizing radiation escaped? Were most of the photons supplied by a few bright galaxies, or by countless faint ones? How often did black holes contribute? The answers are connected. A galaxy may produce many ultraviolet photons, but keep most of them trapped. Another may be less luminous, yet allow a larger fraction to escape. A population of small galaxies could dominate the ionizing budget, even if none is bright enough to study alone. This is why surveys look beyond the most striking detections. The brightest early galaxies are useful because they provide spectra, structure, and detailed physics. But the faint end of the population may control the larger transformation. Astronomers estimate how galaxy numbers change with brightness, then extend that distribution towards sources too weak to detect individually. The extrapolation carries risk. A small change in the assumed number of faint galaxies can alter the estimated supply of ionizing photons. So can a change in their typical stellar populations or escape fractions. Reionization models must therefore combine direct observations with carefully stated assumptions. Gravitational lensing offers one way to reach fainter systems. A massive galaxy cluster can bend and magnify the light from objects behind it. The cluster acts as a natural telescope, increasing the apparent brightness of distant galaxies that would otherwise remain hidden. It stretches images, produces multiple copies, and depends on the distribution of mass in the foreground cluster. Reconstructing the true source requires a lens model, but when the geometry is favorable, lensing can reveal galaxies far below the normal detection limit. These magnified sources may be among the smaller building blocks of the early universe. They are not mature galaxies in the modern sense. Some may contain only a few compact regions of star formation. Others may be pieces of systems that later merged. Their shapes can be irregular, because both the galaxies and the lens distortions are irregular. The first galaxies did not appear as as finished islands of stars. They grew through gas inflow, repeated bursts of star formation, and mergers among smaller halos. Their boundaries were unstable. Their stars formed in dense knots. Their internal motions were still organizing. Some of them may have changed their surroundings in short, intense intervals. A burst of star formation produced ultraviolet light. Massive stars quickly ended as supernovae. Those explosions pushed gas outward and opened temporary channels. Ionizing photons escaped. Then the burst faded, the gas settled, and star formation began again later. A galaxy could therefore contribute to reionization intermittently rather than continuously. This behavior helps explain why an average escape fraction may hide so much variation. The important quantity may not be what a typical galaxy does at one moment, but how often a whole population enters a state that allows radiation to leave. Computer simulations test these possibilities. They begin with dark matter and gas in an expanding universe. They follow gravitational collapse, cooling, star formation, The most detailed models resolve small regions inside galaxies, while larger simulations track the growth of ionized bubbles across broad cosmic volumes. No simulation includes every scale perfectly. The physics of a star-forming cloud unfolds across distances far smaller than the volumes needed to model reionization. Researchers must represent some processes through simplified rules. Different choices can lead to different escape fractions, star formation histories, and bubble sizes. Observations place boundaries around those choices. A successful model must produce enough galaxies at the right times. It must match the brightness distribution of observed sources. It must create ionized regions consistent with quasar absorption. It must produce an optical depth compatible with the microwave background. It must eventually agree with the 21 centimeter signal when that signal is measured clearly enough. Each new galaxy adds another constraint. A secure distance sets a point on the timeline. A spectrum reveals chemical development. A size measurement shows how concentrated star formation may have been. A cluster of nearby sources hints at the environment in which reionization progressed early. The picture becomes less like a sequence of isolated discoveries and more like a network. The galaxies are the bright nodes. The hydrogen between them is the medium they altered. The microwave background records the integrated scattering. The radio sky preserved the neutral gas. The spectra of quasars show where transparency had not yet become complete. From the present, these records are gathered separately. In the young universe, they belonged to one process. A small galaxy formed stars. Its radiation escaped through a broken layer of gas. A bubble expanded. A neighboring galaxy added more light. The boundary moved farther outward. Across enough regions and enough time, those local events changed the state of intergalactic space. Modern telescopes do not watch the whole transformation happen in a single view. They recover pieces of it, a faint red source, a shifted emission line, a lens-stretched arc, a dark interval in a quasar spectrum, a broad polarization pattern, a radio fluctuation not yet fully separated from the foreground. Each piece is incomplete. Together, they are beginning to show how the first galaxies ended an era that had lasted since atoms first formed. The end of reionization was not a curtain lifting across the universe. It was the disappearance of the last large neutral regions from a landscape already filled with light. By then, galaxies had become more common. Their ionized bubbles had expanded far beyond individual systems. In crowded parts of the cosmic web, those bubbles had merged into connected zones spanning enormous distances. Ultraviolet photons could travel through them without immediately meeting a neutral hydrogen atom. The universe was becoming transparent to its own starlight. But even near the end, the change remained uneven. Dense concentrations of galaxies created large ionized regions early. Other places, farther from strong sources, remained neutral. These surviving areas were shaped by the cosmic web, bordered by radiation from several directions, and slowly eroded as the background of ionizing light grew stronger. Astronomers sometimes describe them as neutral islands. The phrase is useful as long as it is not taken too literally. These islands were three-dimensional volumes of hydrogen embedded within an increasingly ionized universe. Some may have extended across millions of light years. Others were narrow remnants between expanding bubbles. Their boundaries were active. Ultraviolet photons reached the edge and ionized the outer layers. Electrons were separated from protons. The exposed gas became transparent to more radiation, allowing the front to advance deeper. At the same time, some electrons recombined with protons, returning part of the gas to a neutral state. Reionization was therefore not simply a one-way count of atoms. It was a competition between ionization and recombination. In low-density regions, once hydrogen became ionized, it could remain that way for a long time because particles rarely met. In denser clumps, electrons and protons encountered one another more often. Those regions could recombine repeatedly and required a continuing supply of ultraviolet photons to stay ionized. This made the final stages demanding. The first bubbles expanded into relatively open space. Later photons had to maintain large volumes while penetrating dense structures that absorbed radiation efficiently. The number of photons produced was only part of the problem. Their paths mattered. A universe filled with stars could still contain neutral pockets if radiation remained trapped inside galaxies or dense gas. Completion required enough ultraviolet light and enough routes through which it could move outward. Feedback shaped those routes. Massive stars heated and disturbed their surroundings. Supernovae pushed gas away from young clusters. In small galaxies, these events could reduce star formation by removing the material needed to make new stars. Yet the same clearing could allow more ionizing radiation to escape. The process could help and hinder itself at once. Radiation also changed the ability of small halos to gather gas. When intergalactic hydrogen was heated, its pressure increased. Gas that might once have fallen into a shallow dark matter halo could remain outside instead. Some of the smallest galaxies may have stopped forming stars efficiently. In this way, reionization may have suppressed part of the population, helping to drive it. Larger galaxies were less vulnerable. Their deeper gravity could hold or reacquire gas. As structure grew, these more massive systems became increasingly important in maintaining the ultraviolet background after the faintest sources began to fade. The end of the Dark Ages was therefore also a change in which galaxies could continue growing. Some early systems brightened briefly and then became fossils. Others merged into larger galaxies and disappeared as separate objects. The galaxies visible around us today are not simple descendants with unbroken identities. They are the results of many combinations. Material from one early halo may now be spread through a large galaxy, locked inside stars, mixed into gas, or carried into a black hole. Their influence survived through inheritance rather than shape. The same is true of the ionized bubbles. No boundary from reionization still hangs in space as a permanent shell. Once the bubbles merged, their edges lost meaning. What remained was a changed intergalactic medium and a background of radiation capable of keeping most hydrogen ionized. This is what the end of reionization means. It does not mean that every hydrogen atom in the universe lost its electron. Neutral hydrogen survived inside galaxies, in dense clouds, and in regions shielded from ionizing light. It remains abundant today. Stars continue to form from it. Radio telescopes map it across the Milky Way and nearby galaxies. The transition concerned mainly the diffuse hydrogen between galaxies. By the time reionization was complete, most of that intergalactic material had been ionized. Ultraviolet light could cross much greater distances. The universe had entered a state closer to the one astronomers observe around later galaxies and quasars. Even then, completion was not a perfectly defined instant. Different observations respond to different thresholds. Quasar spectra may show that long neutral stretches had largely disappeared by one time. Galaxy visibility may indicate that large ionized regions existed earlier. The microwave background gives a broad average. A future 21-centimeter map may reveal isolated neutral structures surviving after the universe was mostly ionized. For this reason, astronomers speak of an ending interval rather than one date. The transition reached its final stages within the first billion years of cosmic history, but its exact timing and duration remain under study. A patchy process can end differently depending on what is measured. One region may become transparent while another remains opaque. One kind of observation may be sensitive to a small remaining neutral fraction, while another is not. A global average can hide local survival. This is why the last neutral islands are scientifically valuable. Their shapes and locations would reveal how ionizing sources were distributed. Large-sized observers would suggest that radiation reached some regions much earlier than others. Smaller remnants would point toward a different mixture of source brightness, escape fraction, and gas density. The end carries information about the beginning. By studying the last places to change, astronomers can infer which galaxies supplied the photons, how far the radiation traveled, and how strongly matter was arranged into the early cosmic web. There is also a thermal memory. Ionized gas was heated. Regions reionized early had more time to cool afterward. Regions reionized late remained warmer for longer. These temperature differences can affect the width of hydrogen absorption lines seen at later times. The intergalactic medium may therefore preserve a faint record of when different regions were ionized, not a visible boundary, not a fossil bubble, a difference in temperature and motion carried forward after the original sources were gone. Observations search for this memory in quasar spectra and the statistical properties of intergalactic hydrogen. Simulations test which reionization histories reproduce the later temperatures and absorption patterns. The result is another layer of reconstruction. Light from quasars traces hydrogen. Hydrogen traces temperature. Temperature traces the arrival of ionizing radiation. And that radiation leads back to galaxies too faint or distant to observe directly. The universe can preserve causes inside consequences. From the place where you are resting now, the night sky gives no visible sign that space was once filled with neutral hydrogen. Starlight crosses the intergalactic medium and reaches the Milky Way from distances that would have been far more opaque during the Dark Ages. That transparency has become ordinary. It allows telescopes to see deep fields crowded with galaxies and lets quasar light carry the chemical signatures of distant gas across billions of years. The conditions for observing cosmic history were partly created by cosmic history itself. The first galaxies changed the medium through which later galaxies would be seen. Their radiation cleared paths for light that had not yet been emitted. By the end, the separate bubbles no longer looked separate. Their edges met, opened, and disappeared into a connected, ionized universe. The last large neutral regions narrowed between them, then broke into smaller remnants, and finally ceased to dominate the space between galaxies. There was no final flash. No universal horizon brightened all at once. The change completed itself through overlap. One region joined another. One channel of transparent gas widened into a network. One isolated island lost its boundary. Across enough time, what had been local became nearly everywhere. The Dark Ages ended not because darkness vanished, but because light could finally travel through the universe that stars had made. The universe that emerged from reionization was not finished. Galaxies continued to merge. Stars continued to form. Black holes grew inside dense and heavier elements spread through gas that had once contained almost nothing beyond hydrogen and helium. The cosmic web became more pronounced as gravity drew matter into filaments and clusters. But one of the oldest transitions had reached its conclusion. The diffuse hydrogen between galaxies was now mostly ionized. Ultraviolet light could travel through distances that had once been closed to it. The first luminous structures had changed not only what the universe contained, but how the universe could be seen. That change still surrounds every astronomical observation. When a telescope gathers light from a distant galaxy, the path between source and observer is part of the measurement. The clarity of that path was shaped by stars that lived long before the sun. Their names are unknown. Their individual light has usually been lost inside larger populations. Yet the state of intergalactic space still carries the result of their existence. The first stars were temporary, their influence was not. Some ended as black holes. Some scattered newly formed elements into their surroundings. Some may have vanished without leaving a bright explosion. Each life was brief beside the age of the cosmos, but together they began a chain of changes that never reversed. The first galaxies inherited those changes. They formed from gas that was no longer perfectly simple. They gathered more matter, produced more stars, and sent radiation beyond their boundaries. Their light met the hydrogen outside them, and it began opening the universe one region at a time. Nothing about the process required a central plan. Gravity gathered matter wherever density was slightly greater. Gas cooled wherever physics allowed it. Stars formed when collapse reached the conditions for fusion. Radiation moved outward when it found a path. From these local events came a transformation on the largest scales. This is one reason cosmic dawn remains difficult to reduce to a single image. The event was not located in one place. It was distributed across the young universe. No observer could have stood outside it and watched the entire pattern unfold. Even now, astronomers do not see reionization as a complete scene. They infer it from overlapping records. A quasar spectrum shows what hydrogen removed. A distant galaxy shows where stars were already forming. Microwave pulsation records the scattering of ancient photons. Radio experiments listen for neutral gas itself. Simulations connect these measurements through gravity, radiation, chemistry, and time. Each record is incomplete, but their incompleteness is different. That difference allows them to support one another. Where one method loses sensitivity, another may remain useful. Where a spectrum follows only one line of sight, a radio map may eventually reveal a broad volume. Where galaxy surveys show the sources, microwave observations constrain their accumulated effect. The history becomes clearer not because one instrument answers every question, but because many limited observations begin to agree. Some questions remain open. Astronomers still work to determine which galaxies supplied most of the ionizing photons. The faintest systems may have played a larger role than the brightest ones, but their numbers and behavior are difficult to measure. The escape of ultraviolet radiation remains uncertain, especially in galaxies too distant to examine in detail. The first stars remain unseen as individuals. Their typical masses are debated. Their formation may have produced single massive objects, small groups, or a mixture that changed with environment. Their explosions and remnants may have influenced early heating and chemical enrichment in ways that have not yet been fully separated. The exact shape of reionization is also still being reconstructed. Its broad progression is known, but the sizes of bubbles, the survival of neutral islands, and the rate at which regions joined remain subjects of active study. The universe has left clues, though not a complete recording. This uncertainty does not return the era to darkness. It gives the darkness structure. It tells us where the boundaries of present knowledge lie and what kinds of measurements may move them. A clearer 21 centimeter detection could reveal the changing distribution of neutral hydrogen. Larger galaxy samples could show how common early sources were. Better spectra could distinguish stellar radiation from the light of growing black holes. Each improvement narrows the space of possible histories. The process is patient because the signal is faint. A photon from cosmic dawn may have crossed expanding space for more than 13 billion years before reaching a detector. By the time it arrives, it carries the effects of redshift, absorption, scattering, and every foreground placed along the path. The act of observing is therefore a careful removal of nearer things. Light from the Milky Way must be separated from radio emission behind it. Instrumental patterns must be distinguished from cosmic structure. Nearby stars must be removed from surveys of distant galaxies. The atmosphere, when present, must be understood. The observer stands inside the universe being measured and must work outward through every intervening layer. There is something fitting in that arrangement. The Dark Ages were ended by light moving through hydrogen. Our understanding of them is being built by following that same light backward. The direction is reversed, but the connection remains. Early galaxies sent radiation outward into their surroundings. Modern instruments receive what survived, Between those two moments lies almost the entire history of structured cosmic time. The Milky Way formed and changed. Generations of stars enriched its gas. The sun condensed from a later cloud containing elements made inside earlier stars. Planets formed from the disk around it. On one of those planets, hydrogen became part of oceans, cells, atmospheres, and instruments to study hydrogen across the universe. The simplest atom became both participant and record. It filled the dark ages. It absorbed the first ultraviolet light. It emitted the 21-centimeter signal. It revealed distant structure through the lines it removed from spectra. And much later, it became part of the observers, asking how the darkness ended. The connection does not require the universe to have been waiting for us. It only requires continuity. Matter changes form. Light keeps moving. Information survives in patterns that can sometimes be recovered. The first stars did not know they were beginning an observable history. Their radiation followed the laws available to it. Hydrogen responded. Electrons moved. Bubbles grew. Galaxies gathered into the developing cosmic web. The meaning came much later, when another part of the universe learned to read those changes. As the final neutral regions diminished, there was no witness to mark the moment. No clock announced that the dark ages were over. The transition became complete only in the broadest sense, across enough volume and enough time that ionized space connected almost everywhere between galaxies. Afterward, the universe remained dark in many places. Most of space still held no nearby star. Night remained night on future worlds. Galaxies were separated by distances filled with little visible light. But darkness no longer meant the absence of luminous structure. It had become the space between stars, the distance between galaxies, and the background against which light could travel. That is the universe we inherited, a cosmos in which the first darkness is gone, though its traces remain. They remain in microwave photons crossing the sky, in absorption carved into quasar light, in faint galaxies stretched into infrared wavelength, in radio frequencies that carry the state of hydrogen before the last neutral islands disappeared. The dark ages did not leave behind ruins. They left conditions. They left boundaries in spectra, patterns in radiation, and unanswered questions spread across time. And now, beneath a later sky, those traces continue arriving. The first light is still on its way.